To motivate our study of heat transfer, we're going to focus on conduction, and this is versus other options like convection. And the key thing about conduction is that it's the form of heat transfer within a solid material. We're going to assume it's a uniform material. We're also going to focus on steady state temperature distributions, and the reason we focus on those is those are what we typically look at for most generic applications. If you imagine an engine running for a while, it reaches steady state. If you imagine a CPU in a computer, it reaches a steady state, and so on. So this covers a wide variety of practical applications. So what governs the physics and the mathematical model of the physics in conduction? Well, if you have a bar which has different temperatures, say cold at this end and hot at this end, then the heat flow that occurs going from the hot down to the cold is going to be captured in what we call Q typically. I just think of that as the heat flow. We're not going to get too focused on the notation in this because we're going to approach this in a different way shortly. But think of Q as the heat flow. And it's driven by a number of elements. One is a material constant, K. One is the cross-sectional area. So the right kind of material flows more quickly. For example, a metal versus an insulator. The wider the cross-sectional area in the material itself, the faster heat will flow. And most important in terms of the fundamentals here, this derivative here, which can be approximated as a change in temperature over a change in position, that captures the drive of heat flow by the temperature difference. The fact that one piece of this long rod here would be hotter than the piece beside it, we could talk about the temperature gradient or derivative there, and the bigger that gradient or derivative is, the more the heat flows along this beam. Now that's some pretty complicated stuff. We are going to try to sneak around this and take it a different approach. We are going to look at a two-dimensional problem because that makes it a little more interesting, but we're also going to approach it in a different way to hopefully simplify the mathematical analysis required. We're going to look at a plate shaped like this, rectangular, or in this case here even just a square plate, and imagine it's sort of a thin three-dimensional thing where we're going to essentially ignore the third dimension. It's going to be constant no matter where we look, and it's going to eventually just cancel out in the steady state equations we're building. What we can do is actually get a temperature function as a function of x and y based on that heat flow equaling 0 over the whole plate. And that heat flow equals 0 is coming from the steady state assumption. Now that is what you might see in a later thermo class. It's pretty complicated to get there. It only works on square or simple shaped plates. There's a whole pile of other limitations to it that we really want to not be constrained by going forward. So we're going to approach this in a different way and cut this plate, which would have a continuous temperature distribution on it. And we're going to cut it into little cells. In this case here, 25 little cells. And we're going to estimate the temperature distribution on this whole plate by assuming the temperature is constant on each cell. Now, is that reasonable? Well, if we took the whole plate, definitely not. But if we take a small piece, I think, all right, well, that's a reasonable approximation because the difference in temperature across this plate isn't going to be large because it's just such a small component of the entire material. So we assume that, and what we're going to be able to do then is estimate the temperature on all these cells and get a temperature distribution for the plate that way. For reference, what we're going to be using is called a finite difference method for modeling the steady state temperatures. What kind of assumptions are we going to need to achieve this? We're going to start off with one, which is that the heat flow into any subsquare is 0. And notice it's the net heat flow. So we might have heat flow in, that's fine, as long as it is matched by heat flow out as well. And that's a perfectly reasonable assumption because that's our steady state assumption. The idea is we've turned an engine on for a while, we've let everything settle down, and we're just looking for the temperature that we get in the long run. So that's pretty reasonable. We then assume that the temperature on any subsquare is uniform or constant, and again, that's reasonable Not quite as good as the other one, but it's reasonable if the temperatures or if the subsquares are small. Squares are small. And there's a subtext there that the smaller the better. We're going to be using an estimate, and the estimate gets better and better if we use smaller squares, very much like calculus ideas of using smaller and smaller delta t's in integrals and derivatives. No heat flows into or out of the insulated side. Just going back a slide, we had an insulated wall on this side, and this is a perfect insulator. Not a great, not a fundamentally flawed assumption. It just simplifies our calculations a bit. And obviously, the accuracy depends on the actual quality of the insulator in a particular scenario. Perfect insulator. So, reasonable. The one other ingredient we're going to bring in is that the heat flow to the environment. So when we say, going back a page again, that we have 20 degrees on the outside, and we're going to have a cell here, there's going to be heat flow from the metal out to that. We're going to assume that that's happening at the same conductive rate as flow within the material. And that's just wrong for fundamental reasons, because this is convection and not conduction. So why would we make that assumption? Purely for illustrative purposes now, it would be easy to fix later on. The equations end up being almost the same, just using different constants for different kinds of heat flow. But it's going to make our life a lot easier just going through the conceptual side if we model everything as conduction. So we're going to stick with this assumption, and we're going to see how looking at this plate shaped in this way is going to allow us to find a steady state temperature distribution on a two-dimensional field like this. To get a sense for how we can model our world using these small segments, these small little subunits, what we can do is draw two of those adjacent cells and talk about the heat flow, again here, that is going to be carried between those two cells. So there's going to be some rate of heat transfer, and it's going to be dependent on the constants, one to do with the materials, one to do with the cross-sectional area, but most importantly, we can approximate this taking the derivative and replacing it with this delta t over delta x, where delta t is in fact just the difference in temperature between these two cells, which we're assuming have one temperature here and one temperature here. So we can simplify that to minus Ka over delta x times Ta minus Tb. This is all constants. Properties, cell size is going to be the same no matter where we look. We're going to pick a nice grid so we get a nice consistent delta x. And what the heat transfer is going to depend on then is just the difference in temperature between this cell and that cell. Now we're going to have to extend that to talk about the heat flow in all directions, but it turns out there's actually only 4 directions that are going to be relevant, because if we're looking for real cross-sectional area contact, only the northwest, south, and east cells are actually going to impinge or have enough contact here, non-zero cross-sectional area contact, with this middle cell, and all of the heat flows are going to boil down to a common constant times the difference in temperature between those cells. That's going to be our gateway for looking at this more complicated scenario as an entity as a whole.